Welcome, everyone. It's wonderful to have you here. Before we get started, would you let us know in the comments where you're tuning in from and the time of day it is for you? I love seeing how this space brings together people from across the globe. A heartfelt thank you as well to all who've subscribed and supported the channel. It helps me know what connects with you, and it helps others discover these calming moments too. And if inspiration strikes, please feel free to leave your ideas for future videos. With that said, let's begin. Chapter 1. Understanding Cosmic Inflation. Cosmic inflation is a concept that transforms our understanding of the universe's beginnings, illuminating the moments just after the Big Bang. Imagine a balloon being rapidly inflated, its surface stretching and expanding. This is akin to what cosmic inflation posits about our universe in its infancy. It suggests that a tiny fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from subatomic scales to across vast distances, far exceeding the speed of light. This dramatic growth addresses many questions that have puzzled scientists: why the universe appears so homogeneous and isotropic, why the cosmic microwave background radiation is so uniform, and why the structures we see today, from galaxies to clusters, emerged in such a seemingly ordered fashion. To grasp the significance of cosmic inflation, we must first explore its historical context. The Big Bang Theory, which emerged in the early 20th century, revolutionized our perspective on the cosmos. Prior to this, the prevailing view was one of a static universe, in which stars and galaxies were eternal. The work of Edwin Hubble in the 1920s, revealing that galaxies were moving away from us, suggested that the universe was expanding. This idea laid the groundwork for the Big Bang Theory, which posits that the universe began from an extremely hot, dense state and has been expanding ever since. While this theory provided a compelling narrative for the universe's evolution, it left certain mysteries unresolved, prompting scientists to seek a more comprehensive explanation. Among those who sought to fill these gaps were Alan Guth and André Linde, two pivotal figures in the development of inflation theory. Alan Guth, in the early 1980s, proposed the idea of inflation as a means to address the shortcomings of the Big Bang theory. He suggested that a brief period of rapid expansion could explain why distant regions of the universe appear so remarkably similar. His work was groundbreaking, as it offered a new framework for understanding cosmic evolution. Guth's insights led to a wealth of theoretical and observational work that would solidify inflation as a cornerstone of modern cosmology. André Linde expanded upon Guth's initial ideas, formulating what is known as eternal inflation. In Linde's model, inflation could continue indefinitely in various regions of space, giving rise to a multiverse, a collection of countless universes, each with its own distinct properties. This notion invites us to consider the vastness of possibilities beyond our observable universe. Imagine gazing into an endless expanse, with each star representing a universe, each with its own set of laws and conditions. The initial evidence supporting inflation theory is as profound as the theory itself. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, a remnant from the early universe. When scientists mapped this radiation, they observed fluctuations and patterns that suggest a uniformity consistent with rapid expansion. These observations align beautifully with predictions made by inflationary models, suggesting that the very early universe underwent a period of extraordinary growth. Furthermore, studies of large-scale structures in the universe, such as galaxies and galaxy clusters, provide additional support for inflation. The distribution of these structures mirrors the density fluctuations that inflation would have created, leading to the formation of galaxies as we see them today. As we contemplate these structures, we can picture them as a grand cosmic orchestra, each galaxy a note in an intricate symphony of existence, created from the echoes of inflation's powerful beginnings. As we immerse ourselves in the story of cosmic inflation, we cannot overlook the profound implications it carries for our understanding of reality. It raises questions that echo through the corridors of time and space. What lies beyond the observable universe? Are there infinite possibilities waiting to be discovered? How does this knowledge reshape our understanding of existence itself? In this vast cosmic landscape, figures like Guth and Linde stand as titans, illuminating the path forward. Their insights not only deepen our understanding of the universe's beginnings, but also inspire a sense of wonder that resonates through each of us. The cosmos, in its complexity and beauty, invites us to explore, to ponder, to dream. As we unravel the threads of cosmic inflation, we find ourselves part of a larger story, one that transcends time and space, weaving together the fabric of our universe. The implications of cosmic inflation extend far beyond mere theoretical musings. They touch upon the very fabric of our existence. The notion that our universe could have emerged from a singular point, expanding so rapidly that it defies our intuition, invites a deeper contemplation of the nature of reality itself. What does it mean for us, as conscious beings, to inhabit a universe that began in such a chaotic, yet structured way? Each day as we gaze into the night sky, we are reminded of the ancient light that has traveled vast distances to reach us. This light carries with it the history of countless stars and galaxies, their formation shaped by the very processes born of inflation. Consider the words of Carl Sagan, who famously said, "The cosmos is within us. We are made of star stuff." This connection to the universe is not merely poetic. It is rooted in the scientific understanding that the elements forming our bodies were forged in the hearts of stars, remnants of the cosmic ballet that began with the Big Bang and was influenced by inflation. Imagine the events that unfolded in those fleeting moments after the universe began to inflate. The rapid expansion would have created a cooling effect, allowing subatomic particles to coalesce into protons and neutrons, the building blocks of atomic matter. This process set the stage for the formation of hydrogen and helium, the first elements that would eventually coalesce into stars and galaxies. Visualize these primordial clouds of gas, swirling and condensing under their own gravity, igniting the first fires of stellar nucleosynthesis. As we delve further into the consequences of inflation, we cannot ignore the significance of quantum fluctuations that took place during this rapid expansion. These tiny variations in density, which arose from the uncertainties inherent in quantum mechanics, served as the seeds for all cosmic structures. Picture these fluctuations as the ripples on the surface of a pond, each ripple contributing to the larger pattern of the universe's evolution. This connection between quantum mechanics and cosmology is beautifully illustrated by the work of physicists like Stephen Hawking, who explored the nature of black holes and their relationship to the fabric of space-time. Hawking's insights challenged our understanding of black holes, suggesting that they might not be the ultimate end of matter, but rather gateways to new realms of existence. Could it be that the very same quantum fluctuations that sparked our universe's expansion also hold the key to understanding black holes? This tantalizing interplay between the infinitesimally small and the grand cosmos serves as a reminder that our quest for knowledge is an unending journey. To further appreciate the significance of inflation, we turn our gaze to the cosmic microwave background radiation once more. This relic of the early universe is not just a faint echo, it is a treasure trove of information. By analyzing the tiny temperature variations within this radiation, scientists can glean insights into the universe's age, composition, and the dynamics of its expansion. Imagine a cosmic archaeologist sifting through the remnants of a primordial explosion, piecing together clues that tell the story of our universe's infancy. The journey of understanding cosmic inflation is marked by collaborative efforts, where the synergy of ideas has propelled our knowledge forward. The work of Guth and Linde has inspired generations of physicists, encouraging them to question established norms and explore new avenues of inquiry. In the realm of theoretical physics, The boundaries of knowledge are continuously being pushed, revealing deeper layers of complexity. Let's not forget the role of experiments in validating these theories. Observatories equipped with sensitive instruments, such as the Planck satellite, have measured the cosmic microwave background with unprecedented precision. These measurements have confirmed many predictions made by inflationary models, providing tangible evidence that supports the theory. Consider the significance of these findings. They not only validate the work of early cosmologists, but also pave the way for future explorations and questions. What mysteries remain to be uncovered in this ever-expanding universe? With each new discovery, we inch closer to answers that have eluded us for centuries. The beauty of scientific inquiry lies in its capacity to reveal the unknown, compelling us to remain curious and open-minded. As we ponder the implications of inflation and its aftermath, we are reminded of the words of Albert Einstein, who said, "The important thing is not to stop questioning. Curiosity has its own reason for existence." Curiosity is the fuel that drives humanity to explore the cosmos, to seek understanding in a universe that is often unfathomable. The questions we ask today may lead to answers that reshape our understanding of existence tomorrow. As we continue to explore the implications of cosmic inflation, we find ourselves standing at the precipice of knowledge, gazing into the vast unknown, eager to uncover the secrets that lie beyond the horizon of our comprehension. In this grand narrative of existence, we are not merely passive observers, but active participants, woven into the very fabric of the cosmos. The story of cosmic inflation serves as a reminder of our place in this intricate web, inviting us to reflect on the interconnectedness of all things. Each star that twinkles in the night sky is a testament to the processes that have unfolded over billions of years, a reminder of the beauty and complexity that arise from chaos. As we contemplate the vastness of the universe, let us embrace the wonder and mystery that it holds. The journey of understanding cosmic inflation is not just about unraveling the secrets of the universe. It is also a journey of self-discovery, an exploration of our own existence within this magnificent cosmos. And in this exploration, we find a sense of peace, a connection to something greater than ourselves, as we continue to seek answers among the stars. The cosmic journey we embark upon through the lens of inflation paints a picture of a universe teeming with potential and mystery. As we ponder the vastness of time and space, it is essential to recognize how the very fabric of the cosmos is intricately woven with the threads of inflationary theory. The rapid expansion that occurred in those early moments not only set the stage for the formation of the universe, but also established the conditions from which all structures arose. Consider the concept of uniformity that inflation introduced. Without this rapid expansion, we might have been left with a universe filled with uneven patches of matter and energy, a chaotic landscape where galaxies could hardly find cohesion. Instead, inflation smoothed out these irregularities, creating a canvas upon which the universe could develop in a more organized manner. The resulting cosmic microwave background radiation serves as a snapshot of this early stage, capturing the essence of a universe that was once a hot, dense soup of particles. The influence of cosmic inflation reaches far beyond its immediate aftermath. As we reflect on the implications of this theory, we can appreciate how it addresses one of the most profound questions in cosmology: the uniformity of the universe. Why is it that distant regions of space, separated by vast expanses, appear so similar to one another? Inflation provides the answer, suggesting that these regions were once in close proximity before being stretched apart. This realization evokes a sense of wonder. Imagine a cosmic thread, once tightly woven, now unfurling to reveal a majestic tapestry of galaxies and stars. Moreover, the notion of eternal inflation opens up a realm of possibilities that challenges our understanding of existence itself. In this model, our universe is merely one bubble in an ever-expanding multiverse. Each bubble may possess different physical laws and constants, leading to a diverse array of cosmic environments. Picture this multiverse as an infinite garden of worlds, where each flower blooms under its unique conditions, some fostering life while others remain barren and desolate. This perspective invites us to question our place in the cosmos. Are we merely a chance occurrence? Or does our universe hold a special significance among countless others? As we journey deeper into the implications of inflation, we must also consider its connection to the fundamental forces of nature. The rapid expansion that characterized the early universe is thought to have been driven by a hypothetical field known as the inflaton field. This field, while still elusive, is central to our understanding of how inflation unfolded. Imagine it as a gentle breeze that pushed the fabric of space-time, creating the expansive universe we observe today. Understanding the nature of the inflaton field could unveil secrets about the fundamental forces that govern the cosmos, unlocking new avenues of exploration in theoretical physics. The search for evidence of inflation continues to inspire scientists as they employ increasingly sophisticated technologies and methodologies. Observational projects like the James Webb Space Telescope are poised to explore the distant reaches of the universe, capturing images and data that could provide further validation of inflationary models. Each discovery adds to the intricate puzzle of our existence, revealing more about the universe's early moments and its subsequent evolution. In this ongoing quest for knowledge, we stand on the shoulders of giants, drawing from the wisdom of those who came before us. The collaborative spirit within the scientific community fosters an environment where ideas flourish and theories are rigorously tested. As we reflect on the contributions of figures like Guth and Linde, we are reminded of the power of intellectual curiosity and perseverance. Their pioneering work laid the groundwork for a deeper understanding of the universe, encouraging future generations to push the boundaries of what we know. As we contemplate the vastness of the cosmos and the intricacies of inflation, we are reminded of the delicate balance between chaos and order inherent in the universe. Each galaxy, formed from the remnants of the rapid expansion, serves as a testament to the beauty that can arise from seemingly random processes. The stars that twinkle in the night sky are not mere points of light. They are luminous beacons, each with its own story to tell, forged in the crucible of cosmic evolution. In this grand narrative, the universe invites us to ponder profound questions. What lies beyond the horizon of our observable universe? What else might exist within this multiverse? And how does it relate to our understanding of reality? As we seek answers, we find ourselves drawn into a deeper exploration of existence, a journey that transcends scientific inquiry and touches upon the philosophical and existential. With each revelation, we are reminded of the interconnectedness of all things. The universe does not exist in isolation. It is a dynamic interplay of forces, energies, and particles that shape the very essence of our reality. As we delve into the implications of cosmic inflation, we uncover a deeper appreciation for the intricate web of life that connects us to the cosmos. In this exploration, let us also embrace the calming beauty that arises from understanding our place in the universe. The knowledge that we are products of an expansive cosmic history can instill a sense of peace and wonder within us. Each time we gaze upon the stars, we are reminded of our shared heritage with the cosmos, an eternal bond that transcends time and space. As we continue to unravel the mysteries of inflation and its far-reaching consequences, we remain steadfast in our pursuit of knowledge. The universe beckons us to explore, to question, and to dream. The journey ahead is filled with promise, inviting us to participate in the ever-unfolding story of existence, where the echoes of inflation resonate through the ages, guiding us toward a deeper understanding of the cosmos and our place within it. Chapter 2: Mechanics of Inflationary Expansion. In the moments following the Big Bang, the universe embarked on a journey of unfathomable expansion. Imagine a balloon, once tightly clenched in your fist, suddenly released. It bursts into an astonishingly large sphere, its surface stretching and swirling into a vast expanse. This is a gentle metaphor for the rapid inflationary phase that transformed our universe from a minuscule point into a vast cosmos, almost instantaneously. This period of inflation was not merely fast, it was exponential. Within an inconceivably brief moment, the universe expanded by a factor of trillions, far beyond anything we can grasp. Visualize the minute fluctuations in energy that were present in the very early universe, akin to tiny ripples on a tranquil pond. These ripples, when magnified by the inflationary process, became the seeds of cosmic structures. Galaxies, clusters of galaxies, and the vast cosmic web that fills the universe today all trace their origins back to these initial fluctuations. At the heart of this inflationary expansion lies a concept known as the scalar field. Scalar fields are quantities that are represented by a single value at every point in space. In the context of cosmic inflation, these fields play a crucial role in determining the dynamics of the universe during its rapid expansion. Picture a field of tall grass swaying gently in the wind. As the wind picks up, the grass bows and bends. Similarly, the scalar field swells and fluctuates, and these variations in energy density drive the acceleration of the universe. One of the most well-known scalar fields in this context is the inflaton field. This theoretical construct is thought to have filled the early universe, creating a vacuum energy that fueled the rapid expansion. The inflaton field, like an unseen force, dictated the behavior of particles and energy during this transformative epoch. As the field oscillated, it released energy, pushing the boundaries of the universe outward, smoothing out any irregularities and setting the stage for the structured universe we observe today. Inflationary theory also offers elegant solutions to several cosmological puzzles. One of the most pressing problems it addresses is the horizon problem. Imagine two distant regions of the universe, separated by vast distances, yet they share remarkably similar properties, such as temperature and density. Traditional Big Bang models struggle to explain how these regions could have come into thermal equilibrium when they were never close enough to interact. Inflation provides an answer. During the rapid expansion, these regions were once in close proximity before being stretched apart, ensuring they shared the same initial conditions. Another conundrum that inflation helps to solve is the flatness problem. The universe appears to be remarkably flat, with its density closely matching the critical density needed to prevent it from either collapsing in on itself or expanding forever. Traditional models suggested that any deviation from this critical density would have grown over time, leading to a universe that is either open or closed. Inflation, however, stretches the fabric of space-time, driving any initial curvature toward flatness. This smoothing effect ensures that the universe's geometry remains as flat as we observe it today. Furthermore, inflation addresses the structure formation problem. The large-scale structure of the universe, with its peaks and valleys of galaxies and clusters, can be traced back to the quantum fluctuations in the inflaton field. These minuscule variations, magnified by inflation, seeded the formation of galaxies and clusters, leading to the rich structure we see in the cosmos. Contrasting this with traditional Big Bang models, we find that they often fall short in explaining the uniformity and structure of the universe. The classical Big Bang theory posited a continuous expansion, but lacked the mechanisms to account for the observed isotropy. Without the smoothing effects of inflation, the universe would appear much more clumpy and chaotic, lacking the remarkable order we observe today. The profound implications of inflation extend beyond mere theory. Renowned physicist Alan Guth, the pioneer of inflationary cosmology, once noted, "The universe is like a giant loaf of bread, expanding as it bakes." This analogy highlights the dynamic nature of space-time and the processes that shaped our universe. As we explore these concepts, we begin to appreciate the intricate interplay between energy and structure, between time and space. Imagine standing on a vast, open plain, gazing up at the stars. Each twinkling light represents not just a distant sun, but countless possibilities and stories of formation. The mechanics behind this grand expansion remind us of the delicate balance of forces that shapes our reality. The universe is not merely a backdrop, it is a living, breathing entity molded by the very fabric of physics. The journey of inflation is one of elegance and complexity, where simple scalar fields orchestrate the vastness of space. As we delve further into these mechanics, we uncover the underlying symmetries and patterns that govern cosmic evolution. Each discovery peels back another layer of mystery, revealing the intricate dance of creation that has unfolded over eons. The understanding of inflation has transformed our perception of the cosmos. It allows us to weave together the threads of observation and theory, crafting a narrative that speaks to the very essence of existence. As we ponder these concepts, we might ask ourselves, what lies beyond our current understanding? What further wonders await in the depths of cosmic exploration? In this ever-expanding quest for knowledge, we find ourselves not just as observers, but as participants in the unfolding story of the universe. Each question leads to another, and each answer unveils yet more mysteries. The mechanics of inflationary expansion is but one chapter in this grand saga, one that invites us to explore deeper and reach further into the cosmos. As we reflect upon these mechanics, let us take a moment to appreciate the quiet beauty of the universe around us. The stars above are not just distant suns. They are reminders of the profound processes that have shaped our reality. Each twinkle represents a story of creation, an echo of the inflationary symphony that created the cosmos we call home. In this vast expanse, we find not only our origins, but our place within the grand tapestry of existence. The rapid expansion of the universe, a phenomenon known as inflation, was a pivotal moment in the cosmic timeline. This extraordinary event not only shaped the universe's structure, but also influenced the very fabric of space and time. In the blink of an eye, regions that were once intimately connected were thrust apart, leading to a scenario where the universe became vast and seemingly homogeneous. Consider how this would feel. Like being in a crowded room, suddenly finding yourself alone in an endless hall, the echoes of familiar voices fading into the distance. At its core, inflation was driven by energy fluctuations within the scalar fields. These fields, like the hidden currents of a deep ocean, exert profound effects on the universe's dynamics. The inflaton field, in particular, is believed to be responsible for this rapid expansion. As it underwent changes, it released energy that propelled the expansion forward, much like a powerful gust of wind that propels a kite into the sky. This dynamic interplay between energy and the expansion of space-time is a fascinating aspect of modern cosmology. As we explore the implications of inflation, we encounter several fundamental questions. How did inflation alleviate the universe's early inconsistencies? What mechanisms were at play that allowed for such a dramatic transformation? The answers lie in the very nature of the inflaton field and its interactions. Inflation not only smoothed out the chaotic fluctuations of the early universe, but also set the stage for the formation of the structures we observe today. The minuscule variations in the inflaton field, amplified during inflation, acted as the seeds for galaxies and cosmic structures. Imagine these fluctuations as tiny pebbles dropped into a still pond, creating ripples that reach outwards, eventually leading to the formation of vast islands in the water. Each of these islands represents galaxies, clusters, and even larger cosmic structures that we see scattered throughout the universe. The contrast between inflationary and traditional Big Bang models is stark. The classical model, while groundbreaking in its own right, struggled to explain the universe's uniformity and structure. It depicted a universe expanding from an initial singularity, but lacked the mechanisms to handle the fine-tuning needed for isotropy. In essence, the classical model painted a picture of a universe that would be chaotic and uneven, filled with regions of varying densities. Yet our observations show a universe that is remarkably uniform on a large scale, with minuscule fluctuations that led to the formation of the structures we observe. This understanding has profound implications for how we view cosmic evolution. The leading theorists, including figures such as Alan Guth and André Linde, have shaped our comprehension of this phenomenon. Their work articulates a vision of a universe that is constantly unfolding, driven by the dynamics of scalar fields. The elegance of their theories lies in their ability to weave together disparate observations into a coherent narrative, one that resonates with the intricacies of the cosmos. As we reflect on these themes, we might consider the implications of inflation on our own existence. If the universe expanded so rapidly, what does this say about our place within it? The very air we breathe, the stars we gaze upon, all originate from the processes that took shape in those early moments. Each atom in our bodies traces back to the stars that forged them, echoing the profound truth that we are intimately connected to the cosmos. The inflationary model has not only provided clarity, but has also ignited new questions. What are the limits of this expansion? Could there be regions of the universe where inflation continues to influence the fabric of space-time? As we ponder these possibilities, we uncover a deeper understanding of the universe's potential paths. The very nature of inflation suggests that our universe may not be the only one. It opens the door to multiverse theories, where countless other universes may exist, each shaped by its own unique set of physical laws. The exploration of inflation leads us to consider the future of cosmological research. With advancements in technology and observational techniques, we are poised to gather more data about the cosmic microwave background radiation and the large-scale structures of the universe. These observations will refine our understanding of inflation and its role in shaping the cosmos. As we continue to seek answers, we remain aware of the beauty inherent in this scientific journey. The universe, with its vastness and intricacy, invites us to explore not only its structure, but also the very nature of reality itself. The mysteries of inflation remind us that the cosmos is a symphony of energies and forces, ever expanding and evolving. In this wondrous exploration, we find that the art of questioning is as vital as the answers we seek. Each scientific inquiry propels us forward, while each discovery deepens our connection to the universe. The mechanics of inflationary expansion serve as a reminder that we are participants in this grand narrative. And, as we gaze into the night sky, we are not merely looking outward, but also reflecting inward, contemplating our own existence within this vast cosmos. The quest for knowledge is woven into the very fabric of our being, and as we delve deeper into the mechanics of inflation, we are reminded of the delicate balance of forces that governs our reality. The universe is a magnificent canvas, and the stories it holds are waiting to be uncovered. Each question leads to new horizons, and each revelation brings us closer to understanding the beauty and complexity of the cosmos. Together we embark on this journey, where the past, present, and future of the universe intertwine, creating a narrative that transcends time and space. The mechanics of inflationary expansion is a chapter filled with wonder and discovery, inviting us to explore further, to dream bigger, and to embrace the mystery that is the universe. Chapter 3. Observational Evidence for Inflation. The universe, in its grand and intricate design, whispers its secrets through the cosmic microwave background radiation, often referred to as the CMB. This faint glow, an echo of the universe's infancy, fills the cosmos with a gentle warmth. Imagine standing on a quiet beach, listening to the soft lapping of waves. The CMB is akin to that soft sound, a persistent hum that carries the history of the universe since the moment it was born from the fiery embrace of the Big Bang. The CMB is a relic of that early state, created when the universe cooled enough for protons and electrons to combine and form hydrogen atoms. This moment, known as recombination, allowed photons to travel freely through space, marking the beginning of the universe's transparency. Imagine a fog lifting, revealing a landscape that had been hidden. The CMB provides a snapshot of the universe just a few 100,000 years after the Big Bang, a time when it was still a hot, dense soup of particles. As we peer into this ancient light, we find a remarkable uniformity with slight fluctuations that hint at the seeds of structure in the universe. These fluctuations are not mere noise. They are the fingerprints of the inflationary period, revealing how the universe inflated and evolved. The anomalies and signatures within the CMB have become a critical focus for astrophysicists, offering clues to the mechanisms of inflation itself. What do these anomalies tell us? Picture a calm lake disturbed by a gentle breeze, creating ripples across the surface. In a similar way, the CMB holds tiny fluctuations that arise from quantum fluctuations magnified during inflation. These variations in temperature across the CMB map are the remnants of those primordial disturbances. They embody the very essence of the inflationary theory, illustrating how regions of space that were once causally connected became vastly separated due to exponential expansion. By analyzing these fluctuations, scientists have painted a detailed picture of the early universe, revealing its composition and the physics at play. The rich tapestry of data collected from missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and more recently, the Planck satellite, has provided unprecedented precision. These missions have meticulously mapped the CMB, allowing researchers to decode the universe's earliest moments. Imagine standing at the edge of a vast forest, where each tree represents a point in space, and the patterns of leaves indicate the interplay of forces that shaped them. The findings from the CMB reveal fundamental truths about the universe's structure, including the proportions of dark matter, dark energy, and normal matter. As astrophysicist Andrew Lang remarked, "The cosmic microwave background is a treasure trove of information about the early universe." These insights extend to the formation of large-scale structures, serving as a bridge between the primordial fluctuations and the sprawling web of galaxies we observe today. The density variations in the CMB acted as the gravitational seeds from which galaxy clusters and filaments emerged. Picture a piece of bread, where the air pockets represent these density fluctuations. As the bread rises in the oven, those pockets expand, leading to a fluffy, airy structure. Similarly, the early density differences grew under gravitational influence, leading to the complex arrangements of galaxies and galaxy clusters that populate the universe. We often wonder, how did these initial fluctuations translate into the grand cosmic web we now observe? The answer lies in the interplay of gravity and time. Over billions of years, regions of higher density exerted gravitational pull, attracting surrounding matter and leading to the formation of galaxies. The voids we see today, vast expanses devoid of galaxies, are the remnants of areas that did not attract enough matter to form structures. Consider the work of renowned astronomer Vera Rubin, whose pioneering studies on galaxy rotation curves provided evidence for dark matter. Her findings illustrate how galaxies, despite their visible mass, rotate at speeds that suggest the presence of unseen mass. This unseen mass is deeply intertwined with the early fluctuations in the CMB, reinforcing the notion that inflation set the stage for the universe's architecture. Recent discoveries from telescopes like Planck and WMAP have illuminated the cosmic stage with remarkable clarity. The Planck satellite, with its advanced sensitivity and resolution, has produced a detailed map of the CMB that has refined our understanding of the universe's age, composition, and the rate of its expansion. Imagine a painter meticulously adding layers to a canvas, each brushstroke revealing a clearer picture. The data from these missions has allowed scientists to refine the parameters of the inflationary models, providing a more nuanced understanding of the forces that govern the early universe. As we contemplate these findings, we begin to see the universe not just as a collection of stars and galaxies, but as a dynamic, evolving entity shaped by its history. The CMB serves as a time capsule, a glimpse into the universe's past, and a key to unlocking its mysteries. What lies beyond the CMB's gentle glow? The answers may reside within the vast territories of the universe's large-scale structure, where galaxies cluster and interact, revealing the ever-evolving nature of cosmic evolution. The CMB anomalies guide us, offering a directional compass as we explore these cosmic expanses, leading us to further understand the intricate web of connections that bind galaxies together. In this journey of discovery, we find ourselves reflecting on the process of scientific inquiry. The work of scientists like George Smoot and John Mather, who were awarded the Nobel Prize for their contributions to the studies of the CMB, reminds us of the power of curiosity and perseverance. They once stated that, quote, "The universe is a very big place," reminding us to embrace the vast unknown as we seek to understand our origins. As we stand at this intersection of data and theory, we are invited to visualize the universe in its infancy, a swirling mass of energy and potential. The vastness of space around us, filled with galaxies, stars, and the faint glow of the CMB, is a testament to the processes that began with a singular moment of inflation. The story of the universe is still being written, chapter by chapter, with each observation adding depth to our understanding. The CMB, with its intricate patterns and subtle anomalies, continues to reveal its secrets, guiding our exploration into the cosmos. Through the lens of advanced telescopes and the dedication of countless researchers, we inch closer to unraveling the complexities of the universe and our place within it. As we embrace this narrative, let us remain open to the mysteries yet to be uncovered, knowing that each discovery brings us one step closer to understanding the cosmos and, ultimately, ourselves. The anomalies within the cosmic microwave background radiation offer a fascinating glimpse into the very fabric of the universe. As we analyze these subtle variations, we uncover the intricate details of inflationary signatures that may hold the key to understanding the universe's early moments. Imagine these anomalies as the faint echoes of a cosmic symphony, each note resonating with the history of creation, a delicate reminder of the forces that shaped the cosmos. When we examine the CMB, we encounter not just an average of uniformity, but a rich complexity. Each fluctuation corresponds to regions of differing densities, acting as the seeds from which all structure would later blossom. These anomalies are often expressed in temperature variations mapped across the sky, revealing a pattern akin to a cosmic quilt, stitched together by the very forces that governed the inflationary period. The largest of these fluctuations correspond to the regions that would eventually evolve into galaxies and clusters, while the smaller ones hint at the more intricate details of cosmic evolution. One of the remarkable aspects of these findings is their consistency with the predictions of inflationary models. The theory suggests that inflation smoothed out the universe, but also introduced slight variations that would become amplified over time. This interplay of uniformity and diversity is what makes the universe so richly textured. Imagine a serene landscape, where every hill and valley tells a story of geological forces at play, shaping the Earth over eons. In a similar manner, the CMB reveals the underlying forces that crafted the universe's structure. As we explore further, we find ourselves drawn to the connections between the CMB and the large-scale structure of the universe, the grand arrangement of galaxies, clusters, and voids that populate the cosmos. These structures did not simply appear. They were born from the gravitational influences acting on the initial fluctuations observed in the CMB. The gravitational pull of denser regions attracted more matter, leading to the formation of galaxies and clusters over billions of years. Picture a cosmic net, woven from the threads of gravity, capturing the very essence of matter and energy. The correlation between the CMB and large-scale structure is not just theoretical. It has been observationally validated. The clustering of galaxies and the distribution of dark matter align remarkably well with the predictions derived from CMB data. This interplay is beautifully illustrated through the work of astronomers who have painstakingly mapped the positions of galaxies across vast swaths of the sky. They have found that the largest cosmic structures, such as superclusters and voids, mirror the patterns of density fluctuations seen in the CMB. Consider the work of renowned astrophysicist Neil deGrasse Tyson, who eloquently remarked, "The universe is under no obligation to make sense to you." Yet, through the lens of science, we are offered pathways to make sense of these vast cosmic phenomena. The link between the CMB and large-scale structure is a testament to the harmony present in the universe, where the tiniest fluctuations have given rise to the grandest arrangements. Recent advancements in observational technology have profoundly enhanced our understanding of these connections. The Planck satellite, in particular, has pushed the boundaries of precision. Its observations have provided a clearer understanding of the universe's composition, revealing that dark energy constitutes a substantial portion of the cosmos, driving its accelerated expansion. Imagine a vast ocean, with dark energy as an unseen current, relentlessly carrying the universe toward an unknown future. The meticulous data from Planck has also refined our estimates of the universe's age and the rate of its expansion, casting light on the complex interplay of forces that govern cosmic evolution. This refinement of our cosmic parameters has profound implications, offering insights into the fundamental nature of dark matter and dark energy. As we sift through this treasure trove of information, we encounter a universe far more intricate than previously imagined, where every detail is a testament to the beauty of scientific inquiry. How do these discoveries influence our understanding of the cosmos? They compel us to rethink our place within it. The idea that the universe is not only expanding, but that its expansion is accelerating, invites us to ponder the future of this grand expanse. Will it continue to stretch infinitely, or will it eventually collapse under its own gravity? The answers remain elusive, yet the journey of exploration is enriched by the knowledge that each observation brings us closer to understanding these cosmic mysteries. As we draw connections between our observations and theories, the narrative of cosmic inflation becomes more vivid. It is a story woven with the threads of discovery, where each thread reveals a deeper understanding of the universe's origins. The pioneering work done by scientists like Alan Guth and Andre Linde has laid the groundwork for this narrative, as they explored the implications of inflationary theory and its consequences on cosmic structure. Their contributions illustrate the power of human curiosity and the relentless pursuit of knowledge. Reflecting on these ideas, we can visualize the universe as a grand tapestry, where each thread represents a moment of discovery, a piece of data, or a theory that has shaped our understanding. The CMB and its anomalies are but a single thread in this vast narrative, yet they are crucial in illuminating the intricate connections within the cosmos. As we continue to investigate the relationship between CMB anomalies and large-scale structure, we are reminded of the importance of collaboration in scientific exploration. The efforts of international teams of researchers working together to analyze data and refine models exemplify the spirit of unity that drives discovery. This collaborative approach enhances our understanding and strengthens the fabric of scientific knowledge. The universe's mysteries beckon us like distant stars, twinkling in the vastness of space. Each discovery serves as a guiding light, illuminating the path ahead as we seek to unveil the truths hidden within the cosmos. The interplay between the cosmic microwave background and the structure of the universe is a testament to the beauty of scientific exploration as we strive to comprehend the profound history of our existence. In this ongoing quest, we hold within us the potential to unlock new understandings, to challenge existing paradigms, and to embrace the wonder of the universe. Each observation, each anomaly, and each connection brings us one step closer to revealing the intricate dance of forces that shape our reality. The story of cosmic inflation is far from over, and as we turn the pages, we are reminded that the universe has much more to share. Chapter 4. Impact on Cosmic Structure Formation. In the vast expanse of the universe, the influence of inflation on the distribution of galaxies is profound and intricate. Imagine the universe as a vast canvas, its surface marked by the delicate brushstrokes of cosmic forces. During the rapid inflationary phase, the once uniform primordial state was transformed, giving rise to the diverse structures we observe today. These structures, from individual galaxies to sprawling clusters, owe their existence to the density fluctuations that emerged in the early universe. Picture these fluctuations as tiny variations in the fabric of spacetime, like subtle ripples on a calm lake. As inflation took hold, these ripples were stretched across cosmic distances, magnifying their effects and setting the stage for the formation of galaxies. The regions of slightly higher density acted as gravitational wells, drawing in matter over time. Conversely, areas of lower density became voids, expanses devoid of galaxies. This interplay between density and gravity is the essence of cosmic structure formation. These fluctuations are not random, they are the echoes of quantum fluctuations that occurred in the primordial soup of the universe. During inflation, these quantum effects were frozen into the fabric of the universe, creating a blueprint for the distribution of matter. Imagine a sculptor chiseling away at a block of marble, revealing the hidden forms within. Similarly, the inflationary period sculpted the universe, defining the positions and movements of galaxies for billions of years to come. As we explore the cosmos, we observe a vast network of cosmic filaments and voids that form the cosmic web. This web resembles a giant spider's web, intricately woven with threads of galaxies and clusters. The filaments are the densest regions where galaxies are concentrated, while the voids are the large, empty spaces in between. This grand structure is a result of the gravitational attraction of matter, pulling galaxies together over time. Consider the work of astronomers who study the distribution of galaxies in the universe. They have discovered that galaxies are not randomly scattered. Rather, they follow a distinct pattern dictated by the underlying density fluctuations from the inflationary phase. The filaments of the cosmic web trace the paths of gravitational influence, guiding galaxies along their journey through the cosmos. This interconnectedness speaks to the beauty of the universe's design, where every galaxy is part of a larger story. In exploring cosmic structure formation, it is essential to compare inflationary models with observed structures. The predictions made by inflationary theory provide a framework for understanding the universe's large-scale structure. Observations from telescopes and surveys have revealed a remarkable concordance between the theoretical predictions of inflation and the actual distribution of galaxies. This alignment strengthens our confidence in the inflationary model, suggesting that the seeds of structure sown during the brief moments after the Big Bang have indeed blossomed into the intricate cosmos we see today. As we gaze into the night sky, we can imagine the great cosmic tapestry unfolding before us. The galaxies we observe are not isolated entities. They are part of a grand narrative, woven together by the forces of gravity and the initial conditions set forth by inflation. Each galaxy, a luminous island in the vast sea of space, carries with it the history of the universe, shaped by the very same processes that began with the Big Bang. The insights gained from studying the impact of inflation on cosmic structure formation are pivotal. They allow us to understand not just where galaxies are located, but also why they are situated as they are. The delicate balance between the forces of gravity and the expansion of the universe informs us about the evolution of cosmic structures over billions of years. It poses a question: how does the early universe, with its infinitesimal fluctuations, give rise to the magnificent variety of galaxies we see today? As we continue to unravel these mysteries, the stories of outstanding scientists guide us. One such figure, Alan Guth, who proposed the inflationary model, likened the universe to a gigantic balloon, expanding far beyond our imagination. His vision laid the groundwork for a new understanding of cosmic evolution, helping us to see the universe not as a static entity, but as a dynamic and ever-changing landscape. Imagine each galaxy as a chapter in a grand book, with the inflationary period as the prologue setting the stage. The density fluctuations, like the first words written on the page, create the foundation for the unfolding narrative. The cosmic filaments and voids represent the connections and separations of the characters within this story, illustrating the complex relationships that define the structure of our universe. As we reflect on this cosmic journey, we can appreciate the elegance of the inflationary model and its implications for the distribution of galaxies. The universe, in its vastness, is not merely a collection of stars and planets. It is a living testament to the processes that have shaped it over time. The interplay of forces, the delicate balance of density and gravity, and the interconnectedness of cosmic structures all point to a universe that is remarkably ordered, yet infinitely complex. In observing the night sky, we are reminded of our place within this cosmic narrative. Each twinkling star and distant galaxy serves as a reminder that we, too, are a part of this magnificent structure. The essence of cosmic inflation and its influence on structure formation invites us to ponder our existence and our connection to the universe around us. As we delve into the nature of cosmic filaments and voids, we can visualize the grand cosmic web that spans across the universe. The filaments, rich with galaxies, are areas of high density where gravity has pulled matter together over eons. These regions serve as highways for galaxy formation, allowing clusters to form and evolve. The voids, in contrast, are vast expanses where gravity has not been sufficient to gather matter, creating serene spaces in the otherwise bustling universe. This cosmic structure is not static. It is a dynamic interplay of forces. Galaxies move along these filaments, influenced by the gravitational attractions of their neighbors. Imagine a river flowing through a landscape, carving paths, and shaping the terrain over time. The cosmic web acts in a similar manner, guiding the evolution of galaxies and shaping their destinies as they drift through the cosmos. The comparison of inflationary models with observed structures reveals a harmony that speaks to the accuracy of our theories. Observations of the cosmic web have shown that the distribution of galaxies aligns closely with the predictions made by inflationary cosmology. This convergence is a powerful affirmation of our understanding and deepens our appreciation for the processes that govern the universe. In contemplating the vastness of the cosmos, we cannot help but wonder about the future. How will the structures we see today evolve? Will the filaments continue to grow, drawing galaxies closer together, or will the voids expand, creating even larger expanses of emptiness? The answers to these questions may lie in the ongoing observations of the universe as we continue to explore its depths. As we journey through this chapter of cosmic formation, we find ourselves at the intersection of science and wonder. The impact of inflation on cosmic structure formation is a profound narrative that invites us to consider the origin of galaxies, the interconnectedness of the universe, and our place within it. Each discovery brings us closer to unraveling the mysteries of the cosmos, illuminating the pathways forged by the forces of nature. In the end, the story of cosmic structure formation is not merely about the past. It is about the present and the future of our universe. It is a tale of evolution, connection, and the beauty of existence itself. As we continue to explore these themes, we remain mindful of the intricate dance of forces that shape the cosmos, reminding us that we are part of a grand narrative that stretches across time and space, inviting us to marvel at the wonders that lie beyond. The interplay of density fluctuations and gravity gave rise to the cosmic filaments and voids we observe today, creating a grand architecture that defines the universe. These filaments, like the roots of a great tree, stretch across vast distances, intertwining and connecting clusters of galaxies. The voids, on the other hand, serve as the expansive spaces between these structures, offering a contrast that highlights the beauty of the cosmic web. Imagine walking through a forest and noticing how the trees cluster together in some areas, while vast clearings exist in others. This is akin to what we see in the universe, where the distribution of galaxies is far from random. The denser regions are where gravity has been most effective, drawing matter together to form galaxies and clusters. In contrast, the voids are like open fields, vast and empty, waiting for the next wave of cosmic evolution to shape them. The formation of cosmic structure is not merely a tale of galaxies coming together. It is also about the ongoing evolution of these structures. Over billions of years, the gravitational forces acting on these filaments have continued to evolve, pulling galaxies toward one another, creating rich environments for star formation and the emergence of new galaxies. This dynamic dance of attraction is akin to the way rivers carve their paths through the landscape, constantly reshaping the terrain as they flow. As we contemplate the structures that arise from these density fluctuations, we can appreciate the significance of the cosmic web as a reflection of the universe's history. Each filament and void tells a story, a narrative of formation, collision, and evolution. Scientists have employed advanced simulations to study these processes, revealing how the intricate patterns observed in the universe today are a direct result of the initial conditions set during the inflationary phase. Consider the work of cosmologists who have mapped the distribution of galaxies across vast regions of space. Their observations reveal a remarkable consistency with theoretical predictions stemming from inflationary models. This harmony lends credence to the idea that the seeds of structure sown in the early universe have indeed flourished into the complex web we see today. In comparing different inflationary models, researchers have sought to understand the nuances of how these early fluctuations have manifested in the cosmos. Each model offers a unique perspective on the nature of inflation and its consequences for cosmic structure formation. Some suggest variations in the rapid expansion rate, while others propose different mechanisms by which density fluctuations could arise. Imagine standing before a grand painting, each stroke revealing a different aspect of the story it tells. Similarly, the various inflationary models paint a rich picture of the universe's evolution, allowing us to explore the multifaceted nature of cosmic structure. As we analyze the data collected from galaxy surveys and cosmic simulations, we glean insights that deepen our understanding of how the universe has evolved over time. Observations have shown that these filaments and voids align with the predictions of inflationary cosmology in strikingly precise ways. The cosmic microwave background radiation, as a remnant from the early universe, serves as a vital tool for understanding how these structures developed. The slight variations in temperature across the CMB correspond to the density fluctuations that would later become galaxies and clusters. In this way, the interplay between theory and observation forms a loop of understanding, where each informs the other. The alignment between observed structures and theoretical models suggests that the inflationary period was a crucial phase in the universe's evolution, setting forth a cascade of events that continues to shape the cosmos today. As we ponder the implications of this cosmic web, we might ask ourselves, what lies beyond the voids? The vast expanses of emptiness are not merely nothingness. They are regions ripe with potential, where the gravitational forces are subtly at play. Over cosmic time, these voids may gradually fill with galaxies as the universe continues to evolve, demonstrating that even in apparent emptiness, there is a dynamic process unfolding. The exploration of cosmic filaments and voids serves as a reminder of the interconnectedness of all things in the universe. Every galaxy, every cluster, is part of a larger whole, intricately woven together through the forces of gravity and the remnants of inflation. Just as the trees in a forest rely on their roots to thrive, galaxies depend on the cosmic web for their existence and evolution. With each new discovery, we peel back the layers of cosmic history, revealing the intricate patterns and relationships that define our universe. The impact of inflation on the formation of these structures is a testament to the elegance and complexity of cosmic evolution. As we continue to explore these themes, we find ourselves drawn into the story of the cosmos, where each chapter unfolds with new insights and revelations. The journey through cosmic structure formation is not merely an academic pursuit. It is an invitation to wonder at the universe's vastness and beauty. Each filament and void represents a piece of the puzzle that is our existence, urging us to contemplate our place within this grand tapestry. Through the lens of science, we can appreciate the artistry of the cosmos, where every galaxy is a brushstroke on the canvas of infinity, inviting us to dream and explore the mysteries that lie ahead. Chapter 5. Inflation and Quantum Fluctuations. In the fleeting moments following the Big Bang, a remarkable interplay of forces began to shape the universe. Quantum fluctuations, those ephemeral ripples of energy and uncertainty, played a crucial role during inflation. Imagine a serene pond, its surface occasionally disturbed by a gentle breeze. Each ripple that forms is a moment of potential, a unique expression of energy manifesting in the fabric of reality. During the inflationary phase, these quantum fluctuations were not merely transient events. They became the very seeds from which structure would emerge. As the universe expanded exponentially, the conditions within it were ripe for these fluctuations to be magnified. Picture a balloon being blown up rapidly. The tiny imperfections on its surface become exaggerated as it expands. In the case of the universe, regions of slightly higher energy density stretched out, while those of lower density receded. This process was akin to a cosmic symphony, with each quantum fluctuation contributing to the grand composition of existence. The very fabric of space-time was influenced by these fluctuations, setting the stage for the universe's evolution. How does quantum mechanics influence such grand cosmic events? At the heart of this mystery lies the principle of uncertainty, as articulated by physicists who delve into the quantum realm. The uncertainty principle suggests that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This intrinsic uncertainty means that energy levels in the early universe fluctuated in ways that seemed chaotic, yet were deeply interconnected. The universe was a dynamic interplay of probabilities, a cosmic ballet of particles and waves. As inflation progressed, these fluctuations became frozen into the universe's structure. Imagine a sculptor capturing the fluidity of water in a block of ice. Similarly, the rapid expansion of the universe trapped these quantum fluctuations, imprinting them into the cosmic fabric. This transition from a quantum state to a classical state, where the effects of gravity and larger-scale structures began to dominate, was a pivotal moment in cosmic history. In this shift, the once abstract quantum fluctuations transformed into tangible density variations that would give rise to galaxies, stars, and the intricate web of cosmic structures we observe today. The interplay of quantum mechanics and gravity created a landscape where regions of slightly higher density began to attract matter, forming the gravitational wells that would eventually become galaxies. Conversely, areas of lower density led to vast voids, empty expanses within the universe. The implications of these quantum fluctuations extend beyond mere structure formation. They resonate through the cosmic microwave background. This faint afterglow, a remnant of the early universe, carries within it the imprint of those primordial fluctuations. Imagine holding a cherished photograph from a bygone era. Each detail tells a story of what once was. The cosmic microwave background serves as a snapshot of the universe just after it became transparent, capturing the slight variations in temperature and density that emerged from those quantum ripples. These temperature fluctuations, detected by sensitive instruments, reveal a universe that was not uniform, but rather a patchwork of densities that would seed the formation of galaxies. The small variations in the cosmic microwave background are echoes of the quantum fluctuations that occurred during inflation. They provide us with a glimpse into the universe's infancy, a time when it was a hot soup of particles, still coalescing into the structures we recognize today. What does it mean for us to stand in the presence of such ancient light? As we gaze upon the cosmic microwave background, we are peering into the depths of time, witnessing the vestiges of the universe's first moments. This glow, a gentle background hum of creation, speaks to the very nature of existence and the intricate interplay between quantum mechanics and cosmic evolution. Consider the words of those who have ventured into the depths of theoretical physics, exploring the boundaries of understanding. The insights of scientists like Alan Guth, whose pioneering work on inflation reshaped our comprehension of the universe, remind us that the cosmos is a realm of wonder. As Guth once said, the universe is an incredibly big place, and we are lucky to be here. It is a sentiment that resonates deeply as we explore the quantum underpinnings of our reality. In this vast expanse, the transition from the quantum realm to the classical universe is not just a technical shift. It represents a profound transformation. The universe, in its early moments, was governed by the strange and often counterintuitive rules of quantum mechanics. Yet, as inflation unfolded, it transitioned into a state where classical physics could take hold, shaping the cosmos we inhabit today. Imagine standing on a cliff, overlooking a breathtaking valley that was once shrouded in mist. As the fog lifts, the contours of the landscape become clear, revealing the intricate details of the world before you. In a similar way, the transition from quantum to classical allowed the universe to emerge from the obscurity of its infancy into the vast expanse we now explore. The interplay of quantum fluctuations and inflation not only explains the structure of the universe, but also hints at the interconnectedness of all things. Each galaxy, each star, carries within it the echoes of those primordial moments. We are, in essence, made of the same cosmic fabric that once fluctuated in the depths of the early universe. As we ponder these ideas, it invites us to reflect on our place in the grand scheme of things. The cosmos, with all its complexity, is a tapestry woven from the threads of quantum uncertainty and inflationary expansion. It beckons us to explore, to question, and to marvel at the beauty of existence. In this delicate balance between the quantum and the classical, we find ourselves at a threshold of understanding. The dance of particles and waves, of energy and gravity, reveals a universe that is both chaotic and ordered, a realm where the smallest fluctuations can lead to monumental transformations. The story of inflation and quantum fluctuations is not merely a chapter in the history of the universe. It is a narrative that continues to unfold, inviting us to journey deeper into the mysteries of existence. As we continue this exploration, we remain ever curious, ever hopeful, for the wonders that lie ahead. As we explore the profound implications of quantum fluctuations during inflation, we begin to understand how they shaped the very essence of our universe. Imagine the universe as a vast, uncharted ocean, its depths filled with mysteries and potential waiting to be uncovered. The early universe, a turbulent sea of energy and uncertainty, was characterized by these fleeting quantum fluctuations. They were not merely incidental, they were foundational, like the undercurrents that guide a vessel across the water. During inflation, the rapid expansion of the universe amplified these fluctuations, turning the chaotic energy of the quantum realm into the building blocks of cosmic structure. Picture this transformation as a sculptor taking a block of marble, revealing the form hidden within. Each quantum fluctuation, now stretched and shaped by the vastness of inflation, contributed to the density variations that would later evolve into stars, galaxies, and clusters. The transition from quantum to classical realms was not instantaneous. It was a delicate process, akin to the slow emergence of dawn after a long night. As the universe expanded, it cooled, allowing gravitational forces to take precedence over the fleeting quantum effects. This shift marked a crucial point where the randomness of quantum mechanics began to yield to the orderly laws of classical physics. As theoretical physicist Steven Weinberg eloquently stated, "The more we learn about the universe, the more we realize how little we know." This sentiment captures the essence of our quest to understand the universe's evolution from its chaotic beginnings to the structured cosmos we see today. As the classical universe began to take shape, the seeds planted by quantum fluctuations bore fruit. Regions of higher energy density began to gravitationally attract matter, giving rise to the first stars and galaxies. Visualize a gentle snowball rolling down a hill, gathering more snow and growing larger with each revolution. Similarly, these burgeoning structures accumulated matter, growing larger and more complex through the interplay of gravity and motion. The implications of this transition extend further, reaching into the cosmic microwave background, a remnant from the universe's early days. This ethereal glow, a soft whisper of light echoing from the past, carries within it the fingerprints of those primordial fluctuations. Imagine a canvas painted with colors that shift and blend, where each hue tells a story of the universe's infancy. The cosmic microwave background provides us with a snapshot of the universe when it was just 380,000 years old, revealing the tiny temperature fluctuations that arose from quantum ripples. These fluctuations are not just random noise, they are the echoes of the inflationary period, capturing the essence of the universe's early state. Each variation in temperature, each slight deviation in density, represents a clue to the conditions that prevailed during inflation. As we observe the cosmic microwave background, we are not merely looking at ancient light. We are witnessing the remnants of the very process that shaped our universe. As we ponder the significance of these observations, we might ask ourselves, what does it mean to uncover such ancient truths? It means that the universe is not just a collection of stars and galaxies. It is a living testament to the intricate processes that govern existence. The cosmic microwave background serves as a bridge between the quantum and the classical, a reminder that the universe is deeply interconnected, with each element reflecting the history of its formation. Consider the work of physicists like George Smoot, whose research on the cosmic microwave background earned him a Nobel Prize. He described this ancient light as the afterglow of creation, capturing the essence of what it means to study the universe's origins. Through their efforts, we gain insights not only into the cosmos itself, but also into the forces that shaped our very existence. As we continue to explore the implications of inflation and quantum fluctuations, we find ourselves at the intersection of science and philosophy. What does it mean to be part of a universe that has emerged from such chaos? It invites us to reflect on our own existence, our place within the cosmos. Each of us carries within us the echoes of those early moments, intertwined in the fabric of reality. The journey from quantum fluctuations to the classical universe is not just a scientific inquiry, it is a deeply human endeavor. It challenges us to think beyond the confines of our immediate experience, to consider the vastness of time and space. It is a reminder that the universe is a grand and intricate system, where every particle has a story to tell. As we stand on the brink of understanding, we are reminded of the beauty inherent in the cosmos. The delicate balance between uncertainty and order, chaos and structure, reflects the complexity of our own lives. Just as the universe has unfolded over billions of years, so too do our own stories weave through the fabric of existence. In the vast expanse of space, where galaxies swirl and stars are born, the interplay of quantum mechanics and inflation continues to illuminate our understanding of the universe. Each new discovery, each new insight, adds depth to the narrative of cosmic evolution. The quest for knowledge is a journey without end, a path that beckons us to delve deeper into the mysteries that lie ahead. As we contemplate the implications of quantum fluctuations and their role in shaping the early universe, we invite ourselves to embrace the wonder of existence. The universe, once a chaotic sea of potential, has transformed into a beautifully orchestrated symphony of matter and energy. This ongoing exploration encourages us to remain curious, to seek out the connections that bind us to the cosmos, and to revel in the knowledge that we are part of something far greater than ourselves. The unfolding story of inflation and quantum fluctuations continues to inspire awe and wonder, reminding us that in the vastness of the universe, we find not only questions but also the promise of profound answers waiting to be discovered. Chapter 6. The Multiverse Hypothesis. The Multiverse Hypothesis, a concept that unfurls from the fabric of cosmic inflation, invites us to consider a reality that is far grander than our own universe. Building upon the rapid expansion we discussed in the previous chapters, imagine a cosmos where, instead of a single universe, there exists an infinite array of universes, each with its own unique properties and laws. This idea emerges from the very heart of inflationary theory, suggesting that the inflationary process could lead not just to the universe we inhabit, but to an entire multiverse. At its core, the multiverse hypothesis is intricately tied to how cosmic inflation works. During the inflationary phase, regions of space can stop inflating at different times, creating bubbles of space that each develop into distinct universes. Picture a vast and chaotic expanse, where some areas are bustling with rapid expansion, while others have settled into a slow, steady state. Each of these bubbles can have different physical constants, dimensions, and even fundamental forces. Some might resemble our own universe closely, while others could be entirely alien, governed by rules we cannot yet comprehend. One of the most intriguing models of the multiverse arises from string theory, which posits that the fundamental building blocks of the universe are not particles, but rather one-dimensional strings. As these strings vibrate, they give rise to different particles, and, consequently, different forces. The implications of string theory suggest that there could be countless ways these strings can interact, leading to a vast landscape of possible universes. Imagine each string as a note in a cosmic symphony, where the unique combination of notes creates a multitude of melodies, each melody representing a different universe. Another model, known as the many worlds interpretation, springs from the realm of quantum mechanics. In this view, every quantum event branches into its own universe, creating a vast and intricate web of realities. Each decision, each outcome creates a divergent path, leading to a reality where every possibility is realized. Can you envision a moment in your life where you made a choice? In the many worlds interpretation, there exists a universe where you chose differently, where the other potential outcomes play out in their own unique timelines. This notion challenges our perceptions of fate and free will, inviting us to ponder the nature of our existence. The philosophical implications of a multiverse are profound and far-reaching. If our universe is just one of many, what does that mean for our understanding of existence? Does it diminish the significance of our own reality, or does it enrich it, suggesting that we are part of a grander narrative? Philosopher David Lewis eloquently stated, "The world is a vast and complex place, and we must not forget that it is only one of many." This perspective encourages us to embrace the mystery and beauty of existence, even if it extends beyond our immediate comprehension. As we journey through these ideas, we must also acknowledge the current debates and critiques within the scientific community surrounding the multiverse hypothesis. Some scientists argue that the multiverse, while intriguing, lacks empirical evidence. They assert that, without the ability to observe or measure other universes, the multiverse concept remains speculative. Is it truly scientific if it cannot be tested or falsified? This question lingers in the minds of many researchers, prompting lively discussions at conferences and in academic papers. Furthermore, the multiverse hypothesis raises questions about the nature of scientific inquiry itself. If we are to accept the existence of infinite universes, how do we define our own? What does it mean to search for a unifying theory of everything in a landscape where countless versions of reality coexist? The challenge lies in balancing the allure of these grand ideas with the rigorous standards of scientific validation. Yet, amid these debates, the multiverse hypothesis continues to inspire curiosity and wonder. It invites us to stretch our imaginations, to entertain the possibility that our universe is but one thread in a vast cosmic fabric. Consider the implications of such a reality. If every conceivable outcome exists somewhere in the multiverse, what does that say about the nature of choice, chance, and destiny? As these discussions unfold, scientists such as Max Tegmark advocate for an open-minded approach to the multiverse concept. Tegmark posits that the multiverse is not merely a fanciful idea, but a serious contender in our quest for understanding the cosmos. He encourages us to embrace the unknown, stating, "Our universe is a strange and beautiful place, and the multiverse is just another layer of that beauty." Imagine standing at the edge of a vast cliff, looking out over an uncharted expanse. The horizon stretches infinitely, filled with possibilities that tantalize the mind. This metaphor captures the essence of the multiverse hypothesis. The vastness invites exploration, challenging us to seek knowledge in the unknown, while also reminding us of our place within this grand cosmos. As we ponder the multiverse, we find ourselves at the intersection of science and philosophy, where the mysteries of existence beckon us to explore deeper. The multiverse hypothesis, with its myriad implications, encourages us to reflect on our understanding of reality, urging us to consider that our universe, while beautiful and complex, is only one piece of a much larger puzzle. What if we are not alone in our search for meaning? What if, across the tapestry of the multiverse, countless beings are pondering the same questions, grappling with their own existence and the nature of reality? These reflections guide us toward a sense of interconnectedness, suggesting that, despite the vast distances that separate us, we share a common curiosity. In this realm of possibilities, the multiverse hypothesis invites us to embrace uncertainty. It teaches us that while we may strive for concrete answers, the beauty of the cosmos may lie in the questions themselves. As we explore these ideas, we open our minds to the grandeur and complexity of existence, preparing us for the journey that lies ahead. As we continue to explore the depths of the multiverse hypothesis and its implications, we find ourselves at the forefront of a profound conversation that transcends the boundaries of science and philosophy. The questions raised by the multiverse hypothesis challenge us to reconsider our understanding of reality, identity, and the very nature of existence itself. What might we discover as we seek to unravel these mysteries? With the multiverse as our backdrop, we stand poised to delve deeper into the boundless cosmos, embracing the wonder and beauty of the unknown that awaits us. As we explore the intricacies of the multiverse hypothesis, it becomes essential to recognize the various models that have emerged from the inflationary framework. Each model presents a unique perspective on the potential structure of this vast array of universes, and they differ significantly in their implications for our understanding of reality. One notable model is the bubble universe scenario, which arises from the idea that during inflation, different regions of space can inflate at differing rates. This leads to the formation of distinct bubbles, each becoming its own universe, encapsulated within an ever-expanding cosmic foam. Imagine each bubble as a small, isolated world, complete with its own unique set of physical laws and constants. Some may possess the conditions necessary for life, while others remain inhospitable, devoid of the elements that sustain existence as we know it. The concept of eternal inflation adds another layer to our understanding. In this model, inflation never truly ends in some regions of space. Instead, as parts of the universe cease inflating, others continue indefinitely. Picture an endless cascade, where new bubbles are constantly being formed, leading to an ever-growing multiverse. This perspective not only challenges our comprehension of time and space, but also invites us to ponder the nature of creation itself. How does one define the beginning of a universe in a setting where creation is an ongoing phenomenon? The philosophical implications of these models are as profound as their scientific underpinnings. If we accept that our universe is but one of many, it raises questions about our significance within this vast cosmos. Do our actions hold weight in a reality where countless versions of ourselves exist, each making different choices and experiencing diverse outcomes? This notion can be both liberating and daunting. The poet and philosopher Rainer Maria Rilke once mused, "The only journey is the one within." In a multiverse where each choice leads to a branching path, the journey of self-discovery takes on new dimensions, encouraging us to embrace the complexity of our existence. Debates surrounding the multiverse hypothesis are vibrant and multifaceted. Critics argue that the lack of empirical evidence for other universes undermines the scientific validity of the concept. They contend that science thrives on testable predictions and observable phenomena. Without the means to investigate or even identify the existence of other universes, can we consider the multiverse hypothesis a legitimate scientific theory? This skepticism fuels ongoing discussions, pushing scientists to rethink the boundaries of inquiry and the criteria for scientific legitimacy. Yet, proponents of the multiverse hypothesis assert that the very nature of our universe may inherently support its existence. They suggest that the fine-tuning of physical constants observed in our universe could be explained if we inhabit just one of many universes, each with varying laws. This perspective invites us to consider a broader view of cosmic design, one that may not hinge solely on our understanding of perfection, but rather on the multitude of outcomes that arise in an infinite landscape. As we continue to explore these ideas, the contributions of leading thinkers illuminate the conversation. Physicist Brian Greene emphasizes the importance of curiosity, stating that the multiverse hypothesis invites us to embrace the great unknown. This sentiment resonates deeply as it encourages us to remain open to the mysteries that lie beyond our current comprehension. In the realm of philosophy, figures like Steven Weinberg have raised poignant questions about the implications of a multiverse for human existence. If the universe we inhabit is just one option in a sea of possibilities, does that diminish the value of our experiences? Or does it elevate our quest for meaning in a universe filled with infinite potential? Such reflections compel us to grapple with the essence of our reality, to seek understanding not only in what we observe, but also in the profound questions that arise from the multiverse concept. Imagine standing on a shore, gazing out at an endless ocean of possibilities, each wave representing a different universe. The beauty of this metaphor lies in the recognition that, just like the waves, the multiverse is dynamic and ever-changing. It challenges us to contemplate the nature of existence, urging us to consider that our understanding of reality is merely a snapshot of a far grander tableau. While some scientists remain hesitant to fully embrace the multiverse hypothesis, the dialogue it has sparked continues to drive innovation and inquiry. The challenges to traditional scientific methods have prompted the development of new ways to think about the cosmos. Researchers are now investigating indirect evidence that could support the existence of other universes. For instance, anomalies in the cosmic microwave background radiation or the distribution of galaxies might offer subtle hints of interactions between our universe and others. As we ponder the multiverse, we find ourselves not just as passive observers, but as active participants in the quest for knowledge. The multiverse hypothesis encourages us to think expansively, to imagine the myriad possibilities that could exist beyond our immediate experience. It serves as a reminder that the universe is a vast and intricate puzzle, and each piece we uncover brings us closer to a deeper understanding of our place within it. In this exploration of the multiverse, we stand at the threshold of profound inquiry, where science and philosophy intertwine. The questions raised by the multiverse hypothesis invite us to reflect on our existence, the nature of reality, and the boundless curiosities that beckon us to explore further. As we journey onward, we remain open to the wonders that await us, ready to embrace the mysteries of the cosmos with a sense of awe and wonder. Chapter 7. Challenges to Inflationary Theory. In the vast landscape of cosmological theories, the inflationary model has sparked both admiration and skepticism. While it offers a compelling explanation for the homogeneity and isotropy of the universe, it has not gone unchallenged. Critics have raised significant concerns, proposing alternative theories that dare to reshape our understanding of cosmic origins. Among these, cyclic models stand out, suggesting a universe in perpetual cycles of expansion and contraction, rather than a singular birth event followed by continuous expansion. Imagine a grand cosmic heartbeat, where each pulse represents a new cycle of creation, destruction, and rebirth. In this view, the universe oscillates, collapsing into itself only to emerge anew, much like the rhythmic ebb and flow of ocean waves. One of the major criticisms of inflationary theory centers around the issue of fine-tuning. As scientists delve deeper into the intricacies of inflationary models, they often encounter a perplexing aspect. The parameters that govern inflation seem remarkably precise. For instance, the energy density required to trigger inflation must be balanced with extraordinary accuracy for it to unfold as theorized. This fine-tuning raises an intriguing question. Why should the universe possess such specific characteristics? Some theorists argue that this fine-tuning implies a level of design or purpose, while others seek to explain it through the multiverse concept, suggesting that countless universes exist, each with its own set of parameters. In this vast ensemble, it becomes more probable that at least one universe could support conditions favorable for life and inflation. The testability of inflationary predictions has also been a subject of intense scrutiny. While inflation provides a framework to understand the early universe, its predictions can be challenging to verify through direct observation. For instance, inflation posits that certain gravitational waves would imprint a specific pattern on the cosmic microwave background. Yet, observing these waves is akin to finding a whisper in a cacophony of sound. As advancements in technology progress, such as the development of more sensitive detectors, the hope remains that these elusive signals can be captured, lending support to or challenging the inflationary model. The pursuit of this evidence is reminiscent of the age-old quest for understanding, where scientists are driven by an insatiable curiosity to reveal the universe's hidden truths. Ongoing research continues to explore the shortcomings of inflation, venturing into new realms of theoretical physics. Scientists are investigating modifications to the inflationary framework, seeking to address its limitations while preserving its strengths. Some propose alternatives that incorporate ideas from quantum gravity, allowing for a more dynamic and less rigid understanding of the early universe. Imagine a landscape where the rules of physics are not fixed but fluid, capable of evolving as the universe unfolds. This line of inquiry invites us to reconsider our assumptions and embrace the uncertainty that comes with exploring the cosmos. As we ponder the challenges to inflationary theory, it becomes clear that the universe is not a static entity. It is a living, breathing tapestry of ideas and theories, each vying for understanding. The interplay between criticism and innovation is essential in the scientific process, pushing boundaries and encouraging new perspectives. This dynamic environment fosters a spirit of collaboration, where researchers from various disciplines converge to share insights and challenge one another. In the realm of cosmology, the journey is as important as the destination. Each challenge faced by inflationary theory illuminates the path toward deeper understanding, inviting us to explore the cosmos with fresh eyes and open hearts. As we engage with these ideas, we find ourselves not just observers, but active participants in the unfolding narrative of the universe. The challenges faced by inflationary theory serve as a reminder that the cosmos is a vast playground for our imagination and intellect, where the mysteries of existence await our exploration. The exploration of alternative theories to inflationary cosmology reveals a rich landscape of ideas, each with its own nuances and implications. Cyclic models, for instance, propose that the universe undergoes endless cycles of expansion and contraction. This perspective shifts the focus from a singular moment of creation to an ongoing process of cosmic rebirth. Imagine a grand cycle where each iteration brings forth new configurations of galaxies, stars, and life. Such models challenge the conventional narrative of a linear universe, suggesting instead that our cosmos has no definitive beginning or end, merely a series of transformative phases. Key figures in this field, such as Paul Steinhardt and Neil Turok, have contributed significantly to the cyclic model's development. They argue that the universe's history is not a singular event, but rather a dynamic evolution influenced by gravitational interactions. The cyclic model posits that as the universe expands, it eventually reaches a maximum size before contracting under the influence of gravity, culminating in a singularity that triggers a new expansion phase. This raises profound questions about entropy and the nature of time itself. If the universe is constantly recycling, what does this mean for the arrow of time? Is our perception of past, present, and future merely a human construct within this grand rhythm? Moreover, the fine-tuning problem in inflationary models is a question that invites scrutiny and speculation. The delicate balance of parameters required for inflation to occur raises an unsettling possibility. Is our universe merely one of many, each with its own set of initial conditions? This inquiry aligns with the multiverse hypothesis, suggesting that we inhabit a universe that is a result of chance within a vast ensemble of realities. The multiverse view proposes that regions of space can have varied physical laws and constants, leading to an astonishing diversity of universes. In contemplating the fine-tuning issue, one might ask, why does our universe appear so uniquely suited for life? Some theorists propose that what we perceive as fine-tuning could be an artifact of selection bias. We only experience a universe that allows for our existence, leading to the conclusion that other configurations, where life cannot evolve, are simply unobservable. This notion echoes the anthropic principle, which posits that our universe's specific characteristics must allow for the emergence of observers like us. The testability of inflationary predictions is another avenue ripe for exploration. While inflationary theory offers elegant solutions to many cosmic puzzles, its predictions often elude direct observation. For instance, the detectable gravitational waves that inflation predicts could provide crucial evidence supporting the theory. However, these waves are elusive, hidden beneath a symphony of cosmic noise. Scientists continue to refine their detection techniques, employing increasingly sensitive instruments and innovative technologies in their quest to capture these faint echoes of the early universe. The reliance on observational evidence emphasizes a cornerstone of scientific inquiry: the necessity of rigorous testing. If inflation is to maintain its standing within cosmology, it must yield predictions that can be scrutinized and validated through empirical methods. This process mirrors the journey of countless scientific revolutions, where theories rise and fall based on their ability to withstand the scrutiny of observations. As ongoing research delves into the intricacies of inflation and its challenges, new theories emerge that aim to reconcile the shortcomings of previous models. One promising direction involves integrating quantum mechanics with the dynamics of cosmic expansion. This approach seeks to explore how quantum fluctuations might influence the very fabric of spacetime during inflation. Imagine a universe where the rules of physics are not merely rigid parameters, but fluid entities capable of transformation. Such a perspective could illuminate new pathways in our understanding of the universe's birth and evolution. In this ever-evolving landscape of cosmology, the dialogue between established theories and emerging ideas fosters a spirit of innovation. Researchers are increasingly collaborating across disciplines, sharing insights from physics, mathematics, and even philosophy. This collaborative atmosphere encourages the exploration of uncharted territories, where the boundaries between different fields blur, leading to breakthroughs that could redefine our understanding of the cosmos. As we contemplate the challenges to inflationary theory, it becomes evident that our pursuit of knowledge is an ongoing journey. The universe, with all its mysteries, beckons us to look deeper, to question, and to embrace the unknown. Each inquiry, each hypothesis, serves as a stepping stone toward a more profound understanding of existence itself. The challenges faced by inflationary theory remind us that the cosmos is not merely a backdrop for our lives, but an intricate narrative in which we play a part, an invitation to explore the extraordinary within the ordinary. The landscape of cosmology continues to evolve, with researchers tirelessly working to address the challenges posed to inflationary theory. Among the most significant areas of inquiry is the fine-tuning of parameters essential for inflation to occur. This delicate balance raises a multitude of philosophical and scientific questions. What if the universe's precise conditions are not merely coincidences, but rather reflections of deeper underlying principles? Some scientists have proposed that the fine-tuning we observe could hint at a grander mechanism at play, one that governs the laws of physics themselves. This notion invites us to consider a reality where universes with varying laws are not just possible, but perhaps inevitable. Picture a vast library, each book representing a different universe with its unique physical laws. Within this library, some books would describe realms that foster life, while others might detail barren landscapes, devoid of stars and galaxies. In light of these discussions, the cyclic models of the universe gain further prominence. These models suggest that rather than a singular creation event, the universe undergoes an endless series of expansions and contractions. This concept posits that the universe is not merely a one-time occurrence. Instead, it is a recurring phenomenon, much like the seasons that grace our planet. With each cycle, the universe sheds its previous form, emerging anew. The implications of cyclic models extend beyond mere cosmic mechanics. They challenge our very understanding of time and existence. If the universe is eternally reborn, what does this mean for the linear progression of time? How do we reconcile the beginnings and ends of cosmic epochs with the notion of an infinite cycle? Such questions prompt contemplations that reach into the depths of both science and philosophy. To evaluate the testability of inflationary predictions is to engage in a delicate balancing act. The very essence of science lies in its ability to propose hypotheses that can be tested, scrutinized, and validated through empirical observation. Yet, inflationary theory presents a unique challenge. Many of its predictions, especially those concerning gravitational waves, remain tantalizingly out of reach. Imagine being in a dark room, listening for the faintest of whispers among the echoes. It is in this search for clarity that scientists employ cutting-edge technology, hoping to capture the elusive signals left behind by the universe's infancy. The quest for evidence becomes a tapestry woven with determination and ingenuity. Advanced observational methods, such as those employed by the upcoming generation of telescopes and detectors, may soon unveil the secrets hidden within the cosmic microwave background. The potential discovery of these gravitational waves would not only bolster the inflationary paradigm, but could also reshape our understanding of the universe's very fabric. Ongoing research is also exploring alternative routes that might address inflation's limitations while preserving its compelling narrative. Innovative approaches, such as those integrating aspects of quantum mechanics with cosmic dynamics, offer new pathways to understanding the universe's birth. Imagine a universe where quantum fluctuations are not mere byproducts but central players in the cosmic drama. This paradigm shift invites us to envision a reality where the very building blocks of existence are in a constant state of flux, creating a dynamic interplay that shapes the cosmos as we know it. As we immerse ourselves in this exploration, the landscape of cosmology becomes a rich tapestry of ideas, each thread representing a different perspective, a distinct inquiry. The scientific community thrives on this diversity, where collaboration fosters innovation and sparks new avenues of thought. Researchers, like explorers charting unknown territories, share their findings and engage in vibrant discourse, enriching our collective understanding of the universe. The challenges to inflationary theory, far from stifling progress, serve as catalysts for creativity and discovery. Each question posed, each theory debated, brings us closer to unraveling the mysteries of existence. They remind us that the pursuit of knowledge is a journey, one that demands both rigor and imagination. The cosmos beckons us to venture forth, to ask bold questions, and to remain steadfast in our quest for understanding. In this vast expanse, we are not merely passive observers. We are active participants in a grand narrative that transcends time and space, a narrative that invites us to ponder our place within the universe's ever-unfolding story. Chapter 8. Future Directions in Inflation Research. As we gaze into the vastness of the cosmos, we find ourselves at the precipice of discovery, surrounded by emerging observational tools and techniques that promise to deepen our understanding of cosmic inflation. One of the most exciting developments in recent times is the advent of gravitational wave astronomy. Imagine ripples in the fabric of space-time, akin to the gentle waves lapping at the shore of a serene ocean. These ripples are generated by some of the most cataclysmic events in the universe, such as the merging of black holes or neutron stars. Detecting these waves opens a new window into the universe, allowing us to explore phenomena that were previously hidden from us. Gravitational waves carry with them the signatures of events that occurred in the universe's infancy, moments that could illuminate aspects of inflation. As we listen to the faint echoes of these cosmic events, we can begin to piece together a more complete narrative of our universe's birth. The LIGO and Virgo observatories have already made groundbreaking discoveries in this field, revealing the existence of previously unknown black hole mergers. What other secrets might the universe hold, waiting to be unveiled by the next generation of gravitational wave detectors? The potential to observe inflationary signatures embedded within these waves could reshape our understanding of the early universe and provide insights into the nature of dark energy. In tandem with gravitational wave research, the upcoming missions and experiments, particularly the James Webb Space Telescope, promise to revolutionize our approach to cosmic inflation. Imagine a telescope that can peer deeper into the cosmos than ever before, capturing the light from distant galaxies and the faint glow of early stars. This remarkable instrument is designed to observe the universe in infrared wavelengths, allowing us to glimpse the formation of stars and galaxies that occurred shortly after the inflationary epoch. By studying the light emitted from these early celestial bodies, we can glean information about the conditions that prevailed during and after inflation. As we contemplate the capabilities of the James Webb Space Telescope, we might wonder how it will inform our understanding of inflation. The telescope's observations could help us identify the primordial fluctuations that seeded cosmic structure, providing a clearer picture of how galaxies formed in the wake of inflation. Its ability to analyze the atmospheres of exoplanets could also offer insights into the fundamental forces at play in the universe. The rich data collected from this mission will undoubtedly spark new questions and hypotheses, pushing the boundaries of our knowledge. Theoretical advancements in inflationary models are also on the horizon, driven by the interplay between observation and theory. As physicists continue to refine their models, the quest for a more comprehensive understanding of inflation unfolds. One promising avenue is the exploration of various inflationary mechanisms. Some researchers are investigating alternatives to the traditional single-field inflation model, considering the possibility of multiple fields contributing to the inflationary process. This complexity could yield a richer tapestry of cosmic evolution, leading to new predictions that can be tested through observation. Moreover, the concept of eternal inflation is gaining traction in theoretical discussions. This idea posits that inflation may not have ended everywhere in the universe at the same time, leading to regions where inflation continues indefinitely. Imagine a cosmic landscape dotted with bubbles of different ages and properties, each representing distinct universes within a vast multiverse. This model could explain the observed uniformity of the cosmos while also accommodating the diversity of structures we see today. As researchers delve into the implications of eternal inflation, they may uncover novel insights into the nature of reality itself. Potential discoveries that could reshape our understanding are abundant in this evolving field. Consider the possibility of detecting primordial gravitational waves directly, a feat that would serve as a powerful confirmation of inflationary theory. Observing these waves would provide direct evidence of the rapid expansion that occurred in the universe's infancy, offering a tangible link to the events that shaped our cosmos. The implications of such a discovery would be profound, inviting us to re-examine not only the inflationary model, but also the very nature of space and time. As we reflect on the future directions of inflation research, it becomes evident that the interplay between observation and theory is creating a fertile ground for new discoveries. The tools and techniques at our disposal are expanding, allowing us to probe deeper into the universe's mysteries. With each advancement, we inch closer to unraveling the intricate processes that govern cosmic inflation and its impact on the evolution of our universe. In this journey of exploration, we are reminded of the words of a great physicist who once said that the great advances in science usually result from new tools rather than from new concepts. As we embrace the emerging technologies and methodologies in inflation research, we stand on the cusp of revelations that could redefine our understanding of the cosmos. Imagine the possibilities that lie ahead, where each observation could lead to groundbreaking insights, illuminating the shadows of uncertainty that still linger in our comprehension of the universe. As we look forward, we must also remain aware of the challenges that lie ahead. The complexity of the universe and the intricacies of inflation present both obstacles and opportunities for researchers. Theoretical models must continually adapt to incorporate new data, and the quest for a unified understanding of inflation will require collaboration across disciplines. Scientists from astrophysics, particle physics, and cosmology will need to work together, sharing their insights and findings to forge a comprehensive narrative of the universe's beginnings. In this spirit of collaboration, we can envision a future where the boundaries between disciplines blur, leading to a more holistic understanding of cosmic inflation. The challenges we face should not deter us, but rather inspire us to push the limits of our knowledge and imagination. As we endeavor to understand the universe, we are reminded that curiosity is a powerful force, driving us to explore the unknown and seek answers to questions that have lingered for millennia. In this ever-evolving landscape of inflation research, we are called to remain open-minded and adaptable. New discoveries may challenge long-held beliefs and prompt us to revise our theories. Yet it is through this process of inquiry and exploration that we will ultimately uncover the truths that lie hidden in the cosmos. The journey ahead is filled with promise, and as we step into this future, we do so with a sense of wonder and anticipation for the discoveries that await us. As we explore the unfolding landscape of inflation research, we find that the synergy between theory and emerging observational tools is paving the way for groundbreaking advancements. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, will not only observe distant galaxies, but could also help us probe the very fabric of the cosmos, potentially unveiling the mysteries of cosmic inflation. Imagine capturing the faint light from stars that formed billions of years ago, illuminating the pathways that led to the universe we see today. Each photon carries with it a story, a fragment of history that, when pieced together, can provide insights into the conditions that prevailed during the inflationary era. Moreover, the ability of the James Webb Space Telescope to study the early universe will allow scientists to examine the distribution of galaxies and the cosmic web, mapping out how structures evolved in the wake of inflation. What if we could witness the formation of the first stars and galaxies, understanding how they emerged from the primordial soup? This exploration could reveal the influence of inflation on the large-scale structure of the universe, shedding light on the intricate relationships between galaxies and the dark matter that binds them. Upcoming missions beyond the James Webb Space Telescope will also play a key role in advancing our understanding of inflation. Consider the European Space Agency's Euclid mission, designed to map the geometry of the dark universe. This mission aims to explore the interplay between dark energy and cosmic inflation, helping to clarify how these forces shaped the universe's evolution. By examining the distribution of galaxies and galaxy clusters, Euclid may provide critical insights into the growth of cosmic structures and the role that inflation played in their formation. As we ponder these exciting prospects, we must also embrace the theoretical advancements that are reshaping our understanding of inflationary models. The exploration of alternative scenarios, such as the idea of multi-field inflation, invites us to consider a more complex landscape of inflationary dynamics. In multi-field models, various scalar fields interact and contribute to the inflationary process, leading to a rich diversity of possible outcomes. Imagine a symphony where multiple instruments play in harmony, each contributing to a grander composition. This complexity opens up new avenues for research and challenges existing paradigms, encouraging scientists to refine their models and predictions. One particularly intriguing area of study is the relationship between inflation and quantum gravity. As researchers grapple with the unification of general relativity and quantum mechanics, the implications for inflation are profound. Could insights from quantum gravity help us understand the initial conditions of the universe? This intersection of fields may lead to new models that incorporate the effects of quantum fluctuations in a more comprehensive manner. As we venture into this territory, we find ourselves grappling with fundamental questions about the nature of reality itself. Potential discoveries in this domain are tantalizing. What if we could detect the imprints of quantum gravitational effects on the cosmic microwave background? Such findings would not only validate inflationary models, but also offer a glimpse into the underlying mechanics that govern the universe. The prospect of linking quantum gravity with cosmic inflation challenges our understanding and inspires us to envision a universe where the smallest scales influence the grandest structures. As we stand on the threshold of these discoveries, we are reminded that the journey of scientific inquiry is often as significant as the discoveries themselves. Each new observation, each theoretical advancement, contributes to a collective understanding that is both dynamic and evolving. The interplay between observation and theory fosters a rich intellectual environment, one where creativity and curiosity are paramount. In this spirit, we must remain open to the unexpected and embrace the possibility that our current models may need to be adjusted or even overhauled. The history of science is littered with moments where prevailing theories were challenged, leading to profound shifts in understanding. The acceptance of new ideas, even those that may seem radical today, could illuminate paths previously obscured. As we contemplate the future of inflation research, we find ourselves at a crossroads. The convergence of emerging technologies, collaborative efforts among scientists, and the relentless pursuit of knowledge creates a fertile ground for discovery. Imagine a time when our understanding of inflation is not just theoretical, but backed by a wealth of observational data, illuminating the dark corners of the cosmos. The future of inflation research is not merely about answering questions. It is about fostering a deeper appreciation for the complexities of the universe. With every new finding, we inch closer to unraveling the mysteries of our origins. The journey is ongoing, filled with promise and the potential for transformative insights that could reshape our understanding of existence itself. As we embark on this adventure, let us remember that curiosity is the compass that guides us. The questions we ask today will pave the way for the discoveries of tomorrow. With each step forward, we embrace the beauty of the unknown, confident that the universe has much more to reveal. Chapter 9. Cosmic Inflation and Dark Energy. As we continue our exploration of the cosmos, we find ourselves at the intriguing intersection of cosmic inflation and dark energy. Imagine a vast ocean, with waves of understanding swelling and receding, and within that ocean, two powerful currents are at play: the rapid expansion of our universe during its infancy, and the enigmatic force that seems to be accelerating that expansion today. Cosmic inflation, as we have previously discussed, is the theory that the universe underwent an exponential growth spurt just after the Big Bang. This brief yet monumental phase, not only set the stage for the large-scale structure of the universe, but also has profound implications for our understanding of dark energy. Dark energy, that mysterious force driving the accelerated expansion of the universe, presents a puzzle that scientists are still trying to piece together. But what if the clues to understanding dark energy lie within the very fabric of inflation itself? To grasp this connection, we must first consider how inflation can inform theories about dark energy. The inflationary phase was driven by a field filled with potential energy, a state that, in many ways, mirrors the characteristics we attribute to dark energy today. Picture this potential energy as a gentle breeze that stirs the surface of a tranquil lake, subtly influencing the patterns of ripples that form. The energy density during inflation could lead us to understand the nature and origin of dark energy, suggesting that they may not be as separate as they seem. As we ponder this relationship, we might ask ourselves how cosmic inflation can shed light on the phenomenon of cosmic acceleration. The universe's expansion is not merely a relic of its past, it is an ongoing process. Imagine observing a balloon, not just as it inflates, but as it continues to expand over time. Scientists have noted that the universe's expansion is accelerating, a realization that emerged from observing distant supernovae that appeared dimmer than expected. This dimming indicated that they were farther away than they should have been, leading to the conclusion that a force is pulling galaxies apart at an increasing rate. This cosmic acceleration invites contemplation. What is this force? If inflationary models indeed suggest a form of energy that permeates space, could it be that this energy is not just a remnant of the early universe, but a fundamental aspect of how our cosmos operates? Delving deeper into dark energy, we encounter the concept of vacuum energy. Visualize a vast, empty space, devoid of any matter. In the quantum realm, however, this emptiness is anything but still. It is filled with fleeting particles, popping in and out of existence. This phenomenon, known as vacuum fluctuations, hints at a seething energy present even in what we perceive as nothingness. This vacuum energy could play a significant role in the universe's future, potentially driving its continued expansion. Consider the implications of vacuum energy. If the universe is indeed filled with this energy, it raises fascinating questions. What happens to the universe as this energy continues to exert its influence? Some theories suggest that the universe could face a future of endless expansion, stretching into a cold and dark expanse. This scenario, often referred to as the Big Freeze, evokes a chilling image of a cosmos where galaxies drift apart, stars burn out, and the universe approaches a state of uniformity, a vast, silent ocean of space. Yet other possibilities dance on the horizon. In a universe guided by vacuum energy, could there be a chance for new structures to emerge, or for other forces to intervene? The interplay between inflation, dark energy, and vacuum energy creates a rich tapestry of potential futures, each thread woven from the very principles that govern our universe. As we contemplate these concepts, we might reflect on the words of notable physicists in the field. One such thinker expressed that the universe is not only stranger than we imagine, it is stranger than we can imagine. This notion encapsulates the complexity and beauty of the cosmos, urging us to embrace the mysteries that lie ahead. Returning to the connection between inflation and dark energy, we can see how the seeds of cosmic structure, born from the rapid expansion of the early universe, may provide insight into the ongoing expansion we observe today. The fluctuations that once shaped galaxies and stars might also inform our understanding of the very energy that propels the universe outward. Imagine the universe as an intricate clockwork, where each cog and gear affects the others, creating a harmonious movement. Inflation set the stage, establishing the initial conditions and structures, while dark energy influences the trajectory of that movement. The relationship between these phenomena is akin to a conversation, one that spans billions of years and unfathomable distances, where each element contributes to the grand narrative of existence. As we delve further into this relationship, we find that the study of cosmic acceleration and dark energy continues to evolve. Astrophysicists are on a quest, seeking out ways to observe and measure the expansion of the universe with ever-increasing precision. They employ advanced telescopes and observational techniques, peering into the depths of space and time, hoping to unravel the intricacies of dark energy's role in shaping the cosmos. In this exploration, we encounter the concept of the equation of state for dark energy, a relationship that describes how energy density evolves as the universe expands. Imagine an artist's canvas, where the strokes of paint represent the energy dynamics at play. By understanding this equation, scientists can better grasp the nature of dark energy and its potential evolution over time. Could it be that dark energy itself evolves? Some theories propose that as the universe expands, the characteristics of dark energy may change, leading to a variety of scenarios for the future of the cosmos. This idea evokes a sense of wonder and mystery, inviting us to consider the universe as a dynamic entity, one that is alive and continuously changing. As we stand at this crossroads of knowledge, we find ourselves contemplating the broader implications of our discoveries. The potential connection between inflation and dark energy not only deepens our understanding of the universe's past, but also opens doors to envisioning its future. What lies ahead in this vast and intricate cosmos? Will we continue to witness the grandeur of expansion, or could other forces arise to challenge our current understanding? As we explore these questions, we remain reminded of the beauty and complexity of the universe, an ever-unfolding story that invites us to look beyond the stars and consider the profound mysteries that linger in the depths of space. With each revelation, we draw closer to understanding not just the universe, but our place within it. As we ponder the vastness of cosmic inflation and the enigma of dark energy, we begin to appreciate the interplay of forces that shape our reality, creating a narrative that is as awe-inspiring as it is intricate. As we explore the relationship between inflation and dark energy, we must consider the implications of cosmic acceleration more deeply. The universe is not merely expanding, it is doing so at an ever-increasing rate. Imagine a river that flows not just forward, but swells in volume and speed as it moves. This relentless expansion, driven by dark energy, raises profound questions about the fundamental nature of the universe itself. The concept of dark energy remains one of the most perplexing challenges in modern cosmology. Scientists have theorized that this force constitutes a significant portion of the universe's total energy density, yet its exact nature eludes us. What if dark energy is a manifestation of the same mechanisms that powered inflation? Could it be that the universe's expansion is not just a consequence of an initial cosmic event, but rather an intrinsic feature of its fabric? To explore this idea, we can turn our attention to the concept of the cosmological constant, a term introduced by Albert Einstein. Originally conceived as a means to maintain a static universe, this constant has since evolved into a cornerstone of dark energy theories. Imagine a vast stretch of space, where energy density remains constant, exerting a steady influence on the universe's expansion. The cosmological constant posits that this energy is uniformly distributed throughout space, pushing galaxies apart and shaping the cosmic landscape. This steady pressure from dark energy leads us to consider how it interacts with the forces that govern cosmic evolution. The interplay between dark energy and matter is akin to a delicate balance on a seesaw. As the universe expands, the gravitational pull of matter weakens, allowing dark energy to dominate. What does this mean for the future of cosmic structures? Could the very galaxies that formed in the aftermath of inflation be at risk of drifting apart into isolation as dark energy continues to assert its influence? As we ponder these possibilities, let us reflect on the role of vacuum energy, a concept closely related to dark energy. Visualize the universe as a vast and dynamic ocean, where even the emptiest regions are teeming with virtual particles that emerge from the quantum vacuum. These particles, born from the fluctuations of the vacuum, suggests that even in the absence of matter, energy persists. This vacuum energy could provide a mechanism for the universe's accelerating expansion, reinforcing the idea that what we perceive as emptiness is a rich tapestry of potential. The implications of vacuum energy stretch far into the future of the cosmos. If this energy continues to dominate the universe's dynamics, we may be heading towards scenarios that challenge our understanding of existence itself. Picture a universe that expands indefinitely, where galaxies, stars, and planets drift apart in an ever-widening expanse of cold, dark space. This vision, often referred to as the Big Freeze, paints a haunting picture of cosmic isolation, where the night sky becomes increasingly devoid of light. Yet, in the realm of possibilities, various theories emerge, suggesting alternative futures shaped by the very forces we are seeking to understand. Could vacuum energy evolve over time, altering its influence on cosmic expansion? Some speculative theories propose that as the universe continues to expand, the properties of dark energy might change, leading to novel phenomena and interactions. In this dynamically evolving cosmos, we might witness the birth of new structures, or the resurgence of forces that challenge the dominance of dark energy. This interplay of forces evokes the words of a famous physicist who stated that the universe is full of surprises, urging us to remain open to new ideas and possibilities. The exploration of dark energy and vacuum energy compels us to ask, what lies beyond our current understanding? As we continue to observe and measure the universe, we may uncover hidden facets of reality that illuminate our path forward. The quest to understand dark energy and its relationship with inflation and cosmic acceleration is ongoing. Scientists are developing sophisticated models and conducting experiments to gather data that may reveal the underlying mechanics at play. Advanced observational techniques, from deep space telescopes to cosmic surveys, are providing insights into the universe's expansion rate and the distribution of galaxies. Each new discovery contributes to the puzzle, bringing us closer to deciphering the cosmic code. As we stand on the brink of this exploration, we must also reflect on the philosophical implications of our findings. The study of cosmic inflation and dark energy not only enhances our scientific knowledge, but also invites us to contemplate our place in the universe. What does it mean for humanity to exist in a cosmos governed by forces so much larger than ourselves? As we seek answers, we find ourselves drawn into a narrative that transcends mere facts and figures, connecting us to the very essence of existence itself. The relationship between inflation, dark energy, and cosmic acceleration is a reminder of the intricate dance of forces that shape our reality. As we delve into these concepts, we come to appreciate the delicate balance that sustains the universe, a balance that has evolved over billions of years. Each moment of inquiry leads us deeper into the vast unknown, where the boundaries of our understanding expand alongside the universe itself. What awaits us in our quest for knowledge? The cosmos, with its myriad mysteries, beckons us to continue exploring its depths, to question and to dream. As we ponder the future of the universe, we are reminded that every step forward brings us closer to uncovering the secrets that lie within the fabric of space and time. Each revelation, a thread woven into the grand narrative of existence, enriches our understanding and connects us to the cosmos in ways we are just beginning to comprehend. Chapter 10. Cosmic Inflation's Legacy on Cosmology. Cosmic inflation has left an indelible mark on modern cosmology, reshaping our understanding of the universe in profound ways. This remarkable theory, proposing a period of rapid expansion just after the Big Bang, has not only illuminated the origins of the universe, but has also provided a framework that continues to guide scientists in their quest for knowledge. Imagine, if you will, a vast landscape emerging from a dense fog. Inflation acts as the sun breaking through, revealing a world rich with detail and complexity. The impact of inflation can be felt in our comprehension of cosmic history. It offers a narrative that aligns the chaotic beginnings of the universe with the ordered cosmos we observe today. The smoothness of the cosmic microwave background radiation, an echo of the early universe, can be understood as a direct consequence of inflation. By stretching tiny quantum fluctuations over vast distances, inflation lays the groundwork for the formation of galaxies and cosmic structures. Picture the universe's infancy as a blank canvas, where inflation paints the initial strokes that define the grand cosmic picture. As we delve into the implications of inflation, we discover that it serves as a catalyst for future scientific paradigms. New observational technologies, such as gravitational wave detectors and advanced telescopes, are poised to explore the remnants of inflation and its effects on the cosmos. Imagine these tools as finely tuned instruments, capable of capturing the faint whispers of the universe's past. They promise to unveil secrets that have long eluded our grasp, potentially confirming or challenging the very foundations of inflationary theory. The legacy of inflation extends beyond mere theoretical implications. It invites us to reevaluate humanity's place in the cosmos. If inflation indeed set the stage for our universe, what does that mean for our existence? It suggests that we are woven into a much larger narrative, part of a cosmic story that spans unimaginable scales of time and space. This realization can be both humbling and exhilarating. Renowned cosmologist Alan Guth, who first proposed the inflationary model, once remarked, "If inflation is correct, then there are many more regions of space where inflation occurred, and other regions where life could potentially emerge." This statement encapsulates the wonder of inflation's legacy. It challenges us to contemplate the possibility of a multiverse, where our universe is just one of many, each with its own unique laws and properties. The implications of inflation extend into the future of scientific exploration. As we refine our understanding of dark energy and its connection to inflation, we are reminded of the intricate web of forces that govern our universe. Dark energy, that enigmatic force driving the accelerated expansion of the cosmos, may find its roots intertwined with the inflationary phase. The potential energy associated with inflation echoes in the characteristics we attribute to dark energy today. Imagine standing on the precipice of discovery, gazing into the depths of the universe. With each new revelation, we inch closer to understanding the cosmic dance that has shaped our existence. The interplay of inflation and dark energy presents a tantalizing puzzle that encourages us to probe deeper into the nature of reality. In contemplating the legacy of cosmic inflation, we find ourselves at a pivotal moment in the history of cosmology. Its impact reverberates through our understanding of the universe's structure, the birth of galaxies, and the ongoing expansion driven by dark energy. As we explore the vastness of space, we are reminded that our journey is not just about seeking answers. It is also about embracing the beauty of the unknown. What does it mean to be part of a universe shaped by inflation? It invites us to reflect on the nature of existence itself. We are not isolated observers. We are participants in a grand cosmic narrative. The legacy of inflation encourages us to foster a sense of connection with the universe and with one another. As we stand at the intersection of science and philosophy, inflation compels us to question our place within the cosmos. Are we mere accidents of nature, or are we integral to the unfolding story of the universe? This inquiry drives us to explore the connections between the microcosm of our existence and the vast expanse of the universe. Each discovery adds to the rich tapestry of knowledge, weaving together the threads of human curiosity and the mysteries of the cosmos. The future of cosmology is bright, illuminated by the legacy of inflation. As we continue to unravel the complexities of the universe, we carry with us the understanding that our exploration is a reflection of our deepest aspirations to comprehend the cosmos. Inflation has taught us that the universe is dynamic, ever-changing, and filled with wonders waiting to be uncovered. In this journey of discovery, we are reminded that science is not merely an accumulation of facts. It is a path to understanding our place in the universe. The legacy of cosmic inflation instills in us a sense of wonder, inviting us to dream of the possibilities that lie ahead. What new horizons await us as we probe the depths of space and time? As we ponder these questions, we recognize that the legacy of inflation reaches beyond the confines of scientific inquiry. It inspires a sense of unity with the cosmos, urging us to embrace the mysteries that surround us. In every star we gaze upon and every galaxy we observe, we find echoes of the inflationary epoch, a reminder of the extraordinary journey that has led us to this moment. In the embrace of the cosmos, we find solace in the knowledge that our existence is part of a greater whole. Cosmic inflation has forged connections between the smallest scales of reality and the vast expanses of the universe. As we look to the stars, we are beckoned to contemplate not just our origins, but our future, as we continue to explore the boundless wonders of the cosmos. The implications of inflation extend into our shared human experience, weaving a narrative that transcends time and space. It invites us to reflect on our collective journey, one that is marked by curiosity and a desire for understanding. As we share in this cosmic adventure, we recognize that each of us plays a role in the unfolding story of the universe. The legacy of cosmic inflation is one of hope and discovery. It encourages us to reach for the stars, to ask questions, and to seek answers. As we navigate this vast expanse of knowledge, we are reminded that our journey is just beginning, and the cosmos awaits our exploration. In the grand tapestry of existence, inflation has left its mark, shaping our understanding of the universe and our place within it. It compels us to look beyond the horizon, to embrace the unknown, and to cherish the beauty of the cosmos. As we stand together on this shared journey, we are united by the desire to uncover the mysteries of the universe and to celebrate the legacy of cosmic inflation. As we reflect on the impact of inflation, a profound realization emerges. It has not only enhanced our understanding of the cosmos, but has also catalyzed a shift in the way we approach scientific inquiry. The questions once confined to abstract theory now reverberate through the halls of research laboratories and observatories worldwide. Cosmology has transformed from a field of speculation into a rigorous science, where hypotheses are tested against the fabric of nature itself. Imagine a world where each discovery builds upon the last, creating a mosaic of knowledge that reveals the intricate workings of the universe. The legacy of inflation inspires a new generation of scientists to pursue questions that probe deeper into the fundamental nature of reality. What lies beyond the observable universe? How do the mechanics of inflation influence the behavior of galaxies over cosmic time? Each answer opens new doors, leading us into realms of thought previously unexplored. Renowned physicist André Linde, one of the architects of inflationary theory, has remarked on the philosophical implications of our expanding knowledge. The universe, he suggests, is not merely a collection of stars and galaxies, but a dynamic entity, constantly shaping and reshaping itself. This perspective encourages us to view the cosmos not as a static backdrop to our existence, but as an active participant in the fabric of time and space. The legacy of inflation also invites us to visualize the universe as a grand experiment, where each observation serves as a data point in our quest to understand the laws that govern existence. The tools we develop, from advanced telescopes to particle accelerators, are extensions of our curiosity, designed to pierce the veil of the unknown. Picture these instruments as keys, each unlocking a different aspect of the cosmic puzzle, revealing the hidden relationships between matter, energy, and the very nature of space-time. As we venture forth into this new era of exploration, it is essential to acknowledge the role of collaboration in scientific progress. Cosmology is not a solitary pursuit. Rather, it thrives on the exchange of ideas across disciplines and cultures. Scientists from diverse backgrounds come together, sharing insights that enrich our understanding and foster innovation. This collaborative spirit mirrors the interconnectedness of the cosmos itself, where galaxies, stars, and planets influence one another in a delicate balance. With the advent of new technologies, the future of inflation research appears increasingly promising. Imagine the potential of next-generation observatories, equipped to detect subtle signals from the cosmic microwave background, illuminating the remnants of the inflationary epoch. These advancements could lead us to a deeper comprehension of the universe's infancy and the forces that shaped its early moments. As we consider the implications of inflation for humanity's place in the cosmos, we encounter a profound sense of awe and humility. Our existence is intricately woven into the very fabric of the universe, shaped by forces that operate on scales far beyond our immediate perception. This realization encourages us to embrace our role as stewards of knowledge, custodians of the inquiry that connects us to the cosmos. How does this awareness alter our perspective on life, on our relationships with one another, and the world around us? It invites a deeper appreciation for the interconnectedness of all things. Each star, each galaxy, and each human being participates in the vast narrative of existence. This understanding fosters a sense of unity, urging us to work together to unravel the mysteries of the universe while cherishing the fragile beauty of our own planet. In the grand narrative of inflation's legacy, there lies a call to action. It challenges us to remain curious, to nurture the flames of inquiry that have driven humanity's quest for knowledge since time immemorial. The cosmos beckons us to explore, to question, and to seek the truths that lie hidden in the shadows of our understanding. As we contemplate the future shaped by cosmic inflation, we recognize that our journey is ongoing. The questions we ask today will set the stage for the discoveries of tomorrow. Each new insight expands the horizon of our understanding and deepens our connection to the universe. It is a reminder that we are not merely passive observers, but active participants in the unfolding story of existence. The implications of inflation resonate far beyond the realm of cosmology. They touch upon our very essence as human beings, urging us to consider the significance of our place within the cosmos. In a universe filled with untold wonders and mysteries, we are reminded of our potential to contribute to the collective pursuit of knowledge. What legacy will we leave for future generations? Will our curiosity ignite a passion for exploration that inspires others to gaze up at the stars and ponder the mysteries of existence? The legacy of cosmic inflation serves not only as a scientific framework, but also as a source of inspiration that transcends the boundaries of our understanding. As we continue to unravel the intricacies of the universe, we find comfort in the knowledge